What is the object's angular acceleration at t equals 3? Well, velocity time graph, acceleration is slope. T equals 3, we're on this slope. So we're going from the point 2, 60 up here to 6, negative 30 down there. The slope is constant through that whole time, so we can just find the slope of the whole segment, which gets 60 plus 30 over 2 minus 6, so that's 90 over negative 4. And 90 over negative 4 is negative, let's see, 22.5 radians per second squared would be the angular acceleration of the object. Average angular acceleration from 0 to 10, well, that's angular velocity at 10 minus angular velocity at 0 over 10 minus 0. At 10, our angular velocity is 0. At 0, it was 60. So we've got 0 minus 60 over 10 minus 0. Sorry, I wrote 10 minus 10. Does that make sense? Over 10 minus 0, so that's negative 60 over 10. It's negative 6 radians per second squared. Next example, a pinwheel starts from rest, has uniform angular acceleration, and completes 3 rotations in 2.5 seconds. So for something like this, since we have uniform angular acceleration, that means we can use our rotational kinematic equations. Since it starts from rest, we know v naught, or omega naught, is 0. 3 rotations, okay, well, 3 rotations is an angular displacement of 6 pi radians. So then we have angular displacement time, initial velocity, angular acceleration. So that means we can use the time-dependent equation, plug numbers in. We got 6 pi, starts from rest, so that's 0, 1/2 alpha times 2.5 squared, and then we can calculate our angular acceleration. Get that. Our angular acceleration is about 6.03 radians per second squared. What is its final angular velocity? Well, in order to use only the givens, our best bet here is Pratique's equation. Delta theta is 1/2 omega naught plus omega final times time. Omega naught is 0, delta theta 6 pi 1/2 omega final times 2.5. So omega final 6 pi times 2 divided by 2.5 is about 15.1 radians per second. Okay. Likewise, the calculus relationships still exist. Angular position. Oh, wait, what? That's a typo. That should say angular velocity. Sorry. Omega is angular velocity. So what I'm giving by that? Well, angular displacement from angular velocity, that means we take an integral. Delta theta is the integral of omega dt. So we integrate from 0 to 4, 3 minus 2t plus 4t cubed dt. And we go ahead and do our calculus. 3t minus t squared plus, actually that's not very nice, is it? Oh no, that's just t to the 4th. Haha. 0, 4. Plug in 0, we get 0. Plug in 4. What is that? 12 minus 16 plus 4 to the 4th. 256. And so we get 252 radians. Angular acceleration at t equals 2. Well, angular acceleration alpha is the time derivative of angular velocity, the rate of change. So take a derivative, that's negative 2 plus 12t squared. So at t equals 2, that's negative 2 plus t squared is 4 times 12 is 48. So 46 radians per second squared. Average acceleration is delta omega over t. So we just have omega of 5 minus omega of 1 over 4. 5 minus 1 is 4. And I'm just going to use my calculator here. Plug in 5, 3 minus 2 times 5 plus 4 times 5 cubed. That's 493. Minus, plug in 1. 3 minus 2 is 1 plus 4 is 5. So the average acceleration is 122 radians per second squared during that time interval. Alright. Now, with rotational stuff, we can get another alternate version of the centripetal acceleration formula. This is on the formula sheet, just so you know, because we know that tangential velocity is r times omega. So if we plug that in, then we have r squared omega squared. One factor of r cancels out, leaving us with omega squared times r is another way of writing centripetal acceleration. And I think there are a couple things on the homework where that will be more convenient. Now, if an object is rolling without slipping, then the linear quantities of its center of mass are equal to the rotational quantities. So if you think about that, you got this thing that's rolling along, and if you consider what point is on the ground, say it rotates, okay, now a point that's 90 degrees away is on the ground. So you rotate it through 90 degrees of distance, but the distance you've traveled is the same as the arc length along the outside of your object. So we can relate how far the center of mass has traveled to the angular displacement of the edge. And that only works if it's rolling without slipping. If there is slipping, then, obviously you're spinning a little bit, and then the angular displacement of your rolling object is going to be larger than the angular displacement. The arc length along the angular displacement of the rolling object is going to be larger than the distance it actually travels. So it only works if we're rolling without slipping. Right. So when you get a problem like this, car accelerates from 11 meters per second at a rate of 2.4 meters per second squared for 1.3 seconds. Diameter of a tire is 65 centimeters. Determine the angular distance through which the tires rotate. Well, we're given all linear variables. Well, time is time. But we have a linear velocity and a linear acceleration, but we want to find angular distance. We can do the kinematic calculation with either linear or rotational variables, and then convert at some point. So if we want to find angular distance, we can just find distance. Delta x is v naught t plus 1/2 at squared. So delta x is 11 times 1.3 plus 1/2, 2.4 times 1.3 squared. So our linear distance traveled is 16.328 meters. And we know that distance is equal to r theta. R, 65 centimeters, is 0.65 meters, so we divide by 0.65. And then we know our angular distance is 25.12 radians, not per anything, just radians. Okay. The angular speed of the car tires, t equals 1.3, similar thing. We can use a equals delta v over t. So 2.4 equals v final minus 11 over 1.3. So the final velocity of the car is going to be 14.12 meters per second. We know that's equal to r omega, so we divide that by 0.65, and we get that our angular speed is 13.47 radians per second. So if you are rolling without slipping, you can translate back and forth between linear and rotational variables. You can also do the same thing with a point on a rotating object. That's more obviously straightforward. Here's another example of a rotating object. Boy is playing on a merry-go-round in the playground. Merry-go-round starts at rest, then he runs around it while holding it, increasing its speed. He jumps on after applying an angular acceleration of 1.14 radians per second squared while moving through 2 revolutions. What is the merry-go-round's angular velocity? Well, we have an angular acceleration. We have 2 revolutions. That's a displacement. We want to know velocity. We know initial velocity. We can use the time-independent equation. So we got 2 times 1.14. 2 revolutions is going to be 4 pi radians. 2 times 2 pi. Omega final squared minus 0 squared. So we can find that angular velocity. Actually, technically that should say angular speed because we're not given a direction. We don't know what direction he's rotating. 5.35 radians per second. If he sits 1.15 meters from the center, well, we know omega is just, or omega r is equal to v tangential. So 5.35 times 1.51 is going to be his tangential velocity. That comes out to 8.08 meters per second. Total acceleration, if you consider the acceleration of a point or an object moving in a circle, in general that acceleration could have 2 components. You could have a tangential acceleration. You could be speeding up or slowing down how fast you're moving around the circle, and then you also have a centripetal acceleration pointing toward the center of the circle. So the net acceleration is, of course, a combination of those two that you get by summing those 2 vectors. So the magnitude of that acceleration and the tangential and centripetal components of acceleration are always going to be perpendicular to each other by definition, because the tangent is perpendicular to the line going from the center. So we can do that, and we know tangential acceleration is equal to r alpha. We know centripetal acceleration is equal to r omega squared. So we can get this formula for acceleration that's for magnitude of acceleration that's in terms of all rotational variables. Everything has an r squared, so we can pull that out. This is r times square root of alpha squared plus omega to the 4th. So that's something we can use. It's not on the formula sheet, but you'll need it to think about it. So, merry-go-round is sped up from rest, reaching an angular velocity of 8.5 radians per second in 3.2 seconds. Assuming constant angular acceleration, find the acceleration of a point 1.1 meters from the center. At this time, well, we need to know our angular acceleration. We know alpha is delta omega over t, which in this case is going to be 8.5 over 3.2, which I'll divide real quick. So that's 2.65625, and we've just derived that our acceleration is equal to r square root of alpha squared plus omega to the 4th. So we know we're 1.1 meters from the center. We know alpha is 2.65625, and we know omega is 8.5. So we can find the net acceleration of that point, which is going to be about 79.5 meters per second squared.